In this video, we're going to take a look at center of gravity. Now, we mentioned this before when we were dealing with torque a little bit, but now we're going to look at how do we calculate and where do we position the center of gravity of an object. And so first, we need to define the center of gravity. And the center of gravity of a rigid body is the point at which its weight can be considered to act when the torque due to the weight is being calculated. So it's the point where we consider all of the mass to be, so that way we can do these torque calculations. Because really what's happening is every tiny little piece of weight is being affected by gravity, and all of that added together. Now, in order to add all of that together, we need to use calculus. So we're going to avoid that in this course. So we're going to use algebra by saying that all of the mass will be located at one particular point, and that will allow us to move forward in these torque equations. So when an object is symmetrical, so if it has a symmetrical shape, then its weight is distributed uniformly throughout the shape. So that means the center of gravity will be located at the geometrical center. So if we have a length of, this board or door or whatever it is, of L, the center of gravity is going to be located at 1/2 L. So we can say that all of the weight of that object is really just a force concentrated at 1/2 L. And this does work in reality. It's not just an approximation, but the sum of all of the torques of the tiny little pieces of mass do add up to give us all of the mass at that position 1/2 L. Now, if we have more than one mass on an object, or let's say we're distributed so that it's not an even distribution, so our center of mass is not going to be at the geometric center, we can calculate it by looking at our axis of rotation. Now, keep in mind, our center of gravity here is going to be the point at which we can put our finger and this thing's going to balance. Okay? And so we want to find the point where we will have a sum of torque of 0. And so from that, we can come up with this calculation that the center of gravity, the position X, center of gravity, and X is the position away from our axis of rotation here, is equal to all these tiny little torques. These right here are just torques that we're calculating. Okay, that's a torque, and we can add up however many we need divided by all of the forces. And so we have these dots here because this can continue on for however many forces we have, or however many chunks of mass we have in a situation. So in this diagram, we only have 2. So we would say that the weight of this board times x1, so the weight of the board times x1, plus the weight 2 that we have, the weight of the block here, times x2, divide that by the sum of these two weights, and that'll give us our x position for the center of gravity. So let's look at an example using this idea, and it's actually an example that we had in the previous video with this upper arm. And so we have a horizontal arm, and it's composed of 3 separate parts. So we're going to say the upper arm, which weighs 17 newtons, the lower arm, which weighs 11 newtons, and the hand that weighs 4.2 newtons. We want to find the center of gravity of the arm relative to the shoulder joint. So we know that it's not evenly distributed, just by the masses and just by life in general. We know our arms are not one even cylinder. So we want to find where is the center of gravity here of this arm. So we have our distances respective to the different bodies, or the different parts of the arm here. And we have the weights that are given to us for each of those. So we're going to use that formula that we just had in the last slide, and we're going to add up all of the weights times their distance and divide by all of the weights. So if we do that, we have the 17 newtons times the 0.13, or the 13 centimeters, that's the upper arm, and then the 11 newtons times the 0.38, which is the lower arm, and the 4.2 newtons times the 0.61 meters, which is the hand. Divide that by the sum of all of the weights here, and we get a center of gravity at 28 centimeters from the edge of our shoulder. Now, keep in mind, this is not the geometric center, and we should think intuitively, well, it should be left of center here because we have more mass on the left-hand side, so we would expect our center of gravity to be moving to the left slightly, and we see that, yes, that is left of the geometric center. So let's take a look at this conceptual example here. We have an airplane, a FedEx airplane that has a bunch of packages in it. And this is actually a real picture here, and it was loaded to the point where all of a sudden the front wheel started to raise up, and it was resting on the back. And so the issue here, the reason that this happened, is the center of gravity was placed outside of the supports. And so the wheels here cause 2 points of contact with the ground, and as long as the center of gravity of the plane is in between those 2 points of contact, this will stay balanced. But once that center of gravity is placed outside of it, we cause a torque here, and this begins to rotate. And it rotates to the point until it gets another point of contact over here in the tail, so that the center of gravity is in between the 2 points of contact. You're actually doing this every day whenever you walk and stay balanced. Whenever you walk and whenever you're standing, you are maintaining your center of gravity in between your points of contact. If you don't, then you rotate, and which could either cause you to fall or have to change your base or support, whatever it may be. But this is something that we intuitively already know. Any person or any animal that can walk does this on a regular basis. But with inanimate objects, we need to be able to place the center of gravity in between our supports and make sure that we have a sum of the torque that equals 0. Now let's say we have some irregular shape and we want to find the center of gravity of this irregular shape. If we just attach a string to one end of it, we know that because the center of gravity is somewhere in this shape, it's going to cause a torque and a rotation until the point where it settles and the center of gravity is directly below that point of contact. So if we do it at one point, we can attach this irregular object, hang it from a string, and draw a dotted line. And we see that the center of gravity has to be somewhere along this line. Well, if we then attach to another point of contact and do the exact same thing, we know the center of gravity has to be somewhere below that line. And so we see where those two lines intersect, and we get the center of gravity. Now, this is just an essentially two-dimensional object here. If we had a three-dimensional object, then we would want to hang it from a third spot so we could find the exact point where the center of gravity is. Now, this is important if you're trying to find something that you want to balance. You know those people that balance those rocks together, they have an intuitive sense of finding the center of gravity of an object just by feeling it and playing with it. And so they're able to locate the center of gravity, some irregular stone, and place it directly over top of the support structure. And so that's why sometimes we can balance a stone on a very small spot.